Everybody can hear me? All right, so thanks so much for the very generous introduction. Danilo Bzdok, that's pronounced stock as in stock market. And so my research team at McGill and Mila really has the mandate to revisit classic questions in neuroscience and health using, oh, am I sharing this one? Okay, sorry for the remote people. Well, I shared the screen. This is this one. Okay. And so this is there. Okay. So mandate, revisit classic questions in neuroscience and health using emerging machine learning solutions. And that the way we do this is we typically wait for large data sets that didn't exist, that are wider, deeper, richer than what existed before. And then we go in and try to find new ways to attack classic questions from completely new angles. And that is why our research is very wide, and colleagues ask me regularly at cocktail parties what I'm actually doing. So you see some of these examples in 3 different themes on the following slides. So I talked to and compensated by different companies. So why is this intersection of health neuroscience, machine learning particularly attractive now? So what may be clear or not to people in this audience is starting on the left, the highest number of PhD positions funded in absolute numbers is probably in neuroscience. Why is that? So when I finished medical school 10 years ago, there were hardly any large data sets that existed, let's say more than 1,000 people rich. And it was the beginning of these international research consortia. So the European Brain Project started, $1 billion, no, well, it's a French, $1 billion just for research. Then there was a similar development in the United States. And other countries followed up, Japan, Israel, and so on and so forth. And that led to a wave of titanic data sets that we have now, just 10 years later, but oftentimes not so clear, what do we actually do with these massive data sets? And this is where machine learning comes in. So in a parallel development, around maybe 10 years ago, there is this exponential rise in interest and activity in the machine learning space. I show you the plot here with the increasing number of submissions to premium machine learning conferences every year, and that keeps being the case. And of course, those methodologies that come out of the machine learning space, they are exactly what we need to tackle some of these massive data sets that emerged in health and neuroscience. And that really opens the door to a new era in precision medicine or personalized medicine. So why am I saying that? First off, it's interesting to consider that until around 1900, if somebody went to a medical doctor, the life expectancy of that person increased maybe. So I think it's not really clear to the general public that it's just over the very recent decades that medicine started to be evidence-based, driven by data. Randomized clinical trials only emerged in the 50s. So it's not that long that it really have very principled and data-based ways of deciding how to treat a certain disease, treat a certain patient. And so this premium tool, let's just take randomized clinical trials, is based on a case control notion. So there's this binary approach. You have 2 different groups. There's the disease group and the healthy people. And this is what a lot of the knowledge has been derived from. The next step in the 21st century, however, is perhaps maybe to make precise statements about single individuals, the patient in front of you, which is entirely different from this case control setting that we have been in health, including neuroscience, over the last decades and still today. So let me give you an example from what this roughly means in the example of mental health. So a lot of these diseases that we diagnose and treat in mental health here on the left they don't really, as we say, carve nature at its joints. So what this means is that the labels that we have, they are not actually capturing the phenomena that we're actually trying to capture. So, and this is exactly where machine learning shines, because this is a regime of quantitative modeling where we can just put together all these very different, very diverse, complementary views on a same individual, bridging across genetics, life experience. We do studies of thousands of variables of behavior in thousands of families, for example, brain measurements and so forth. We can put all this together and ask machine learning algorithms for us to find meaning and see deeper into these very high dimensional descriptions of single individuals. And just to say this again, just 5 or 10 years ago, we did not have any of those data sets. They just didn't exist. So using this panel C now, we can hopefully get a cleaner description, biologically valid descriptions of disease entities, which would be just a milestone in itself, because that is a necessary prerequisite to then make earlier detections of certain diseases and conditions, try to anticipate what types of treatment may be ideal for a particular person. Let me just emphasize, in mental health, if somebody is suspected to have or diagnosed with something like major depression, you just need to realize that it takes 2 or 3 months to find a treatment most of the time, and it doesn't work in all the cases. It's a trial and error type of approach. So anything that allows us to go away from this will probably be progress in the future. So, and also we may be able to monitor progress using these clear descriptions to, in the end, enable precision medicine by single subject prediction. Okay, so 3 themes of how machine learning helps to make progress towards this goal. So the first is the idea of transfer learning. Let me just give a very simple definition. Oftentimes it means for us, we learn structured knowledge from a large data set that we then carry over to a smaller data set to more effectively mine the smaller resource. So even today, a lot of clinical data sets, they have sample sizes of only in the hundreds or thousands of people. So that is very different from the internet scale regime in which we're in computer vision, convolutional deep nets, or as we see now in large language models. So how can we do this? In this example here, in this paper 5 years ago, we combined pretty much all the brain functional imaging data sets that were out there at the time here on the left. And we tried to fit a deep learning algorithm that tried to distinguish dozens of different activities that people executed in the brain imaging scanner. And so the reason for why we did that is because we wanted to derive a functional atlas of what the territories are in that populate the cerebral cortex of the human brain across completely different task data sets. And so once you have this export product of this project, you can use this to slice and dice data in smaller cohorts, for example, clinical ones that are very hard to obtain. So and this gives you more statistical power for whatever the downstream analyses are. We also try to use YouTube to improve predictions based on brain scans of phenotypes in humans. So why YouTube? If you think about when a radiologist is trained, they already experienced the world in a quarter century. So somebody doesn't start a radiology training at 5 or 15, but in the mid-20s usually. So there's already the visual cortex of those future radiologists has already experienced all these different categories in the natural world. And by the same token, why not fit convolutional deep nets on thousands of videos that have nothing to do with the brain, have nothing to do with the types of phenotypes that we ultimately want to predict. And that actually turns out to work in a number of cases. So we can take deep nets that have been trained on pretty much the entire YouTube and then fine tune them to really identify the patterns that are specific in brain scans, what a radiologist would see, to then make more refined predictions in these 40,000 individuals. So, and at the time, this was the largest existing brain imaging data set in the world. So my favorite transfer learning and last example is this one here. So let me explain this a little bit. When a psychiatrist, child psychiatrist sees somebody, a child who may have autism spectrum disorder, ASD, the way this works is that the children usually see this medical doctor several times, because often it's not possible from a single session to be really sure that a certain child is diagnosed with this condition or not. So what we did here is we really just take the handwritten hospital reports in French, we digitize them, we translate them to English, we clean them to then use them for large language models. These large language models that we use, they have already been trained on millions of reports, on also thousands of articles from the scientific literature in psychology, medicine, and so forth. So there's all this implicit knowledge and semantic understanding of psychology and mental health and medicine that's already embedded in this learning architecture. We then carry this over to, and let me just give the extreme example, let's say 300 reports of the first visit of a child, in all cases of which the medical doctor did not yet know whether he or she will diagnose this child with autism. And the classification accuracies that you see on the left, they are first only. It shows that in 75% of the times, we can predict just from these text reports correctly whether the medical doctor will diagnose this child as autism in the future or not. So there's something about these cues that are in these text reports that is indicative of these features that are relevant to make this diagnosis. And just as a side note, these accuracies, they're actually better than the accuracies that we see based on high-dimensional brain imaging, which is very expensive, or based on genetics, the last 15 years also haven't given better prediction accuracies. So despite all this technology that we have, the most valuable source to make accurate predictions in this particular condition, at least at a single subject level, may be the clinical intuition and machine learning, the clinical intuition of the psychiatrist, the domain expert itself. Okay, second example is diversity-aware modeling. So when me and my colleagues, we saw these always larger data sets, we were excited and we thought, wow, our prediction accuracies are going to get better and better and better, and we'll now finally have the resources to really make concrete steps towards single subject prediction. That's not how the story went. The opposite was the case. So what you see on the x-axis, as we had always larger data sets in brain imaging and mental health, the prediction accuracies across various conditions, that's the colors, actually went down. So there's something about these always more representative, always larger, always less inclusion-exclusion criteria restricted data sets. As we get closer to the actual general population with less artificial case control and healthy groups, it actually becomes always more difficult to actually predict accurately at the single subject level. So we try to understand this better. With collaborators in Singapore and other parts of the world, we looked at two of the largest data sets at the time. And what we did is, across a number of phenotypes related to mental performance that you see on the x-axis there, in children on the right and adults on the left, we fitted models on the entire general population and then applied them in two groups. And that's in green, the white Americans, and in blue, African Americans. And what you can see in all these plots is in pretty much all cases, these predictive models perform much less well, statistically significant less well than the white Americans in all cases. So fitting a model on the largest existing data sets that exist in this space does not allow to make equally well-performing predictions in these different demographic groups. So we try to come up with a way to probe this in an experimental fashion. So, and the way we do this is we use a causal inference framework from epidemiology that has not been used in neuroscience as far as we know. And what we do is we purposefully sample for our training sets in the cross-validation schemes specific degrees of specific demographic strata to see how this impacts the training and the prediction quality of the algorithms. So as a side note, this is what you see on the right side. The most used deconfounding techniques to correct for site differences, demographic differences, socioeconomic differences, they do not actually work, at least for out-of-sample prediction in machine learning. This is what we have shown in this paper. So it's not just the prediction quality. So what you see here is we look inside of these predictive algorithms and we quantify how changing diversities, changing demographic composition, stratification in our training cohorts, how does this actually affect what these predictive algorithms latch onto? And look at the scaling there. So we go down all the way to 0.6, 0.5 similarity in the predictive principles that these learning algorithms have detected and extracted. So what type of demographic strata are part of your training sample has a huge impact on what the machine learning algorithm actually identifies as relevant for prediction. So, and it's not just that, it gets even more complicated because across the input space, in our case, across the cortex, what features are affected by diverging diversity in the training cohorts is not uniformly distributed. So in other words, there are certain parts of the brain that disproportionately change more, yield more brittle predictive principles than others. So, and it turns out that it's the highest evolved parts of the brain, the most recently expanded compared to monkeys, 30 times bigger. It's those parts of the brain that actually keep maturing through adolescence, through early adulthood. It's those parts of the brain that are live wired, maybe a unique aspect of our species. It's those parts that actually give the most brittle predictive principles. And so this is something that we probably need to take into account in the future. Okay, last theme to finish up. Oftentimes, I talk to students and they want to use the latest and most amazing tools. And the question that typically comes up then is, can we actually use this tool that is really hot on Twitter right now for the types of data sets that we actually have that actually exist in our particular space? So I think what we need is careful empirical scaling analyses that benchmark and quantify the feasibility of which regimes of analysis paradigms are actually beneficial for certain predictions. So we conducted the largest deep learning benchmarking study in brain imaging neuroscience a couple of years ago, and we pitted against each other standard linear models in red, nonlinear extensions of those in green, and then hierarchical nonlinear models in blue. And we conduct what's called an empirical sample complexity analysis, where we act as if we had less subjects than we actually have to scale the prediction performance as a function of the cohort training sample size. So, and on the left, you see the scaling. That's the textbook results that everybody would expect. Deep learning models do better than last generation kernel nonlinear methods. And these are doing better than the standard linear models in red. And that's the case pretty much in all sample sizes. That's not what we observed in brain imaging data. This is what you see on the right. So we used the largest existing brain imaging data at the time. This was at the time 10,000 people. We see a collapse of these modeling regimes. So just based on this slide, you can say the scaling behavior of these algorithms in these kind of medical data, they are just not the same. We cannot take these insights from the ISML NERDS community and just carry them over to the medical field. This empirically shows that that's probably not possible. So we then tried all sorts of feature selection techniques. I'm not going to go into details. So we tried to attack these data from all sorts of different perspectives. We did not see a lot of divergence between the linear, the nonlinear, and the hierarchically nonlinear modeling regimes in our scaling analyses. And so here's some clues why that may be. We then went back to this benchmark data sets from the machine learning community here on the left. And we deliberately added noise to one of the favorite data sets that people look at, the MNIST data set. And what you see across these panels is as we add always more noise to the machine learning data set, we see this collapse of these modeling paradigms exactly as we saw in the medical data. So that's not a definitive proof, but it shows clues that noise may be part of the reason why, just imagine an X-ray and imagine a natural image of a dog. There's just a difference in the quality of detail that we have in these kinds of data. So, but here's some positive news. We collaborated with people at Charité Berlin, used even larger brain imaging data sets that merged in the meantime. And we tried to extrapolate towards sample size of 1 million people. And we do see small increases in the prediction performance in this very large modeling regime, in this large sample regime, sorry. But the question is, of course, as a society, do we want to pay? Do we really want to stem this logistic effort to get increases of a few % of accuracy? Is this really necessary? So this concludes my third theme of examples of studies that I run in my lab. And I hope I convinced you that there is value in putting machine learning solutions to questions in neuroscience and health. We can oftentimes not use those tools out of the box, just download it from GitHub and apply it to the medical data set. That's not how it works most of the time. There's a lot of work that's necessary to adapt these core machine learning contributions to the domain questions that we really have. And so, however, if we succeed in doing this, we could go beyond this classic case control binary setting that has served us well to make progress towards single subject predictions that would be faster, more cost effective, and more pragmatic. So I thank my partners, and I thank these institutions for the financial support. Okay, any questions?
Thank you very much, Danilo. I just have a quick question for you on the end, because you mentioned that it's difficult to take an out of the box and have that solution. But if partners would want to interact with some of the research that you're doing or learn how to kind of have those steps, how would you go about, or how would you suggest to them to work with?
How to do this?
Yeah.
I think in my limited experience, you need a tailored approach. So for each data set, for each research question, it's different. So this is why, just very concretely, in my lab, we have a completely different analysis pipeline in every single project. So the way we try to do it, our approach is to be a little bit the spider on the web. We collaborate with domain experts who have 20, 30 years of experience in a certain area. We can speak their language. We work with core machine learning experts. We can speak their language too. And we kind of mediate, having two caps at the same time, wearing two hats. We try to mediate between them to kind of ping pong back and forth, iterative solutions towards something that, in my experience, is most of the time tailor-made.
Thank you very much.
Okay. Thanks so much.
Thank you very much, Danilo.